nanohub.org.
So now we're moving, we're taking the atom molecule interaction forces. We're going from those models, we're going to apply those now to tip sample interaction forces, right? So this just summarizes what we discussed in the last lecture. Just sort of a pictorial idea of the different forces that could be present between the tip and the substrate. The last three forces, last three interactions on this slide are the ones that are most important for atomic force microscopy. And what we're going to try to do in this lecture is we're going to try to show you how to take those forces and integrate them over solid objects to get net interactions. So perhaps the simplest way to think about this is to have, let's say, an atom or a molecule at this red dot, which is labeled zeta equal to 0, and then separated from that atom or molecule is a large flat plane, right? The surface-to-surface separation of the plane from the atom or molecule is this parameter small d, right? So that's the relevant separation distance. We're going to assume that the atom or molecule interacts with the atoms in the substrate by an interaction potential. We're going to model that interaction potential as minus a constant c divided by r sub n. N is going to be an integer. And at the end of the day, we're going to let n equal to 6 because that's what we found for the van der Waals interactions. Okay? We're going to assume in the process of adding up all the forces between all the atoms that make up the substrate with that one atom suspended above the substrate, when we add all those things up, we're going to just use calculus, which means that we're inherently assuming that there's an additivity of the net interaction forces of all the atoms in the substrate with that one atom in the tip, right? That neglects all kinds of things, right? It neglects the fact that the atoms in the substrate could vary with position. It neglects the fact that there are atoms on the surface which could be completely different than atoms in the bulk. But that's the assumption we're going to make. Okay? So the other thing we have to deal with is we have to deal with the number density of atoms in the substrate. So this number density in the discussion that follows is signified by this constant rho, which is the number density, not the mass density of the atoms in the substrate. So rho means how many atoms there are per cubic meter, because the interaction forces, these van der Waals interaction forces, are between individual atoms or molecules, right? So we have to use a special definition for rho that's somewhat different than the standard definition. And so the argument is pretty simple. We're going to take this assumed minus c over r to the n interaction energy, and we're going to integrate that systematically over the entire substrate. We're going to do that by breaking the substrate into little rings, right? The radius of the ring is this parameter x. The thickness of the ring is dx. The thickness of the ring in the y direction is dx. The thickness of the ring in the zeta direction is d zeta. So the total number of atoms enclosed in this ring is just going to be rho times the volume of that ring, dv. And so I work out what dv is in terms of the relevant geometries. And so if we Since all the atoms in the ring are at this constant distance from the molecule, which is located at zeta equal to 0, we can then write down a simple formula for the interaction force of all the molecules in the ring with that one red molecule at zeta equal to 0. That interaction is going to be a constant c divided by r sub n, and that r sub n is going to be just the square root of zeta squared plus x squared, as I've got indicated. So as we let x vary from 0 to infinity, we take into account all the molecules, all the atoms in the substrate at a fixed distance zeta from the atom or molecule, and then to take into account the fact that the substrate could have a depth to it, right? We have to integrate from zeta equals d to zeta equals infinity. So there's two integrals involved. And when you do all that arithmetic, you end up with a formula, right, which I've got written down, and then you can evaluate that formula for arbitrary n. We're going to pick n equal to 6 because that's the van der Waals force. That's the van der Waals interaction. And so at the end of the day, what we find is that the interaction between this one atom or molecule suspended a distance d away from a flat substrate that's infinitely large, that interaction energy is proportional 1 over d cubed with some numbers. Pi, c, rho. Rho is the number density. This quantity 6 is just a result of the integration that's indicated in the first line of this slide. Okay? So that's how you go from individual interactions between atoms or molecules and one atom interacting with a whole plane of atoms or molecules. Okay? Yeah.
So the letter C is related to the van der Waals forces, and the letter C that we saw.
Yeah, C is a constant, which is the sum of the Keesum, the Debye, and the London interactions. Okay, and technically, if you want to know what C is for atom A and atom B, you've got to go and you've got to do a very detailed calculation using those formulas that I showed at the end of last lecture. Practically speaking, those calculations have only been done for certain simple atoms and molecules. So we know roughly what the range of C is, right? We know the order of magnitude range of C, but for individual atom sitting above a substrate.
Because C varies with the distance.
Well, C varies with...
It's varying as I move the angle.
Well, C varies with the interaction between the dipoles. So you have to tell me, does this atom, this red atom, does this have a net dipole moment? Right? If it has a net dipole moment, then I think I have to include the Keesum terms. If it doesn't have a net dipole moment, right, it could maybe have an induced dipole moment. So then I have to calculate the polarizability of that atom, right?
I'm trying to understand why you take out C from the integral. Because
C is a constant, right? C is a constant. So, right, we're approximating the atom-atom or molecule-atom interaction by this U of R equals minus C over R to the N. The R to the N is suggested by the discussion in the previous lecture. N is going to be 6 to capture the van der Waals interaction. This constant C just lumps together all those other things that are very messy, right? And experimentally, we like to get maybe a value of C, right? We'd like to find a handbook or a table where all values of C are listed for all possible atoms and molecules, but don't hold your breath, right? Those numbers are not there, right? So in a sense, the previous lecture just sets up that assumption that U of R equals minus C over R to the N. The minus sign means it's attractive. The C means there's some number. And the N is 6 to capture van der Waals forces. Right? So I just wanted to say it's sometimes hard to find these number densities for different elements, right? So there's a solid state physics textbook that's very well known by written by Cattell. I think it's in its 8th or 9th edition by now, but if I have the 5th edition, right? You go to page 32, for every element, they list these number densities, right? So these number densities are indicated by the numbers in these red boxes, And they're on the order of 3 to 4 times 10 to the 28th atoms per cubic meter for all the elements in the periodic table. So just to give you a sense of what that number is. And if you ever need those numbers, you can always refer to Cattell. So, the first example was the simplest example you can think of. It's just one molecule outside of a substrate, a flat substrate. The next more relevant calculation is let's model an AFM tip as a sphere. And let's suspend that sphere a distance small d above a flat substrate. And let's use this same interaction potential, minus c over r to the n, to calculate what the net interaction between that sphere is in the substrate. Okay? So one formula that we're going to keep using over and over again is this formula that's written in red, right? This is the result that comes when you try to calculate the number of atoms in the tip, which is modeled as a sphere, versus the number of atoms in that flat substrate. So we'll use that formula in red about 2 or 3 more times during the course of the lecture. In this case, you have to work out an expression for the number, right? You need to know the number of molecules in this thin disk, which is indicated by a white slab in the middle of this sphere. The radius of that disk is x. That disk is located at a distance zeta plus d from the substrate, and you're going to clearly integrate that disk over the entire shape of the tip, which in this case is, we approximate the tip as a sphere, right? So you can check the arithmetic later, but I think you'll find that at the end of the day, right, you'll end up with a formula that says the interaction energy between the sphere and the tip varies as d to the n minus 5. That's the important thing. We then substitute n equals 6 for van der Waals forces, so we got 1 over d to the 6 minus 5, that's a 1 over d force. And so at the end of the day, we find that the interaction between a sphere and a flat substrate that's infinitely big, that interaction varies as 1 over the surface-to-surface separation d, right? The radius of the tip is involved, right? This number 6 in the denominator just comes from evaluating all those terms, n minus 2, n minus 3, n minus 4 for n equal to 6, right? And we get a number, this characteristic number, pi squared c times rho squared, okay? And that number is now going to be called the Homaker constant. All right, so from now on, we're going to approximate pi squared c times rho squared is a number h. And so h is this famous Homaker constant that you always see referred to in the literature. Different textbooks use different symbols for Homaker constants. So sometimes you'll see the Homaker constant written as A, capital A. Sometimes you'll see it written as capital A sub h. Sometimes you'll just see it as written as capital H. But that Homaker constant is trying to capture the essence of this van der Waals interaction between 2 atoms, 1 atom in the tip, 1 atom in the substrate. That's the parameter C. And it also takes into account the density, the number density of the atoms in the tip and the substrate. That's this parameter rho squared, right? And when we do this calculation, if you want to actually evaluate the Homaker constant, right, you have to know C and you have to know the number densities, right? You have to know the C and you have to know the number density. But you will find tables of Homaker constants that have been either experimentally determined or theoretically calculated. Those tables are available in the literature, okay? That number determines how strongly the tip interacts with the substrate. So it's an important idea, right? So, couple of obvious things. I hope they're obvious, right? If the tip and the sample are made of different materials, the calculation I did assumed the tip and the substrate were the same materials. So we use the same number density rho. If they're different materials, you have to replace rho squared by the product of rho 1, rho 2, where rho 1 is the number density of the atoms in the tip, rho 2 is the number density of atoms in the substrate, right? We assume the tip is a homogeneous sample. The reason we assume it's a homogeneous sample is so we can apply calculus. We can apply integral calculus. So we're assuming that everywhere inside that tip, everything is uniform. If it's not, then you can't integrate over the shape of the tip, right? We're also assuming that this Homaker constant, or that this van der Waals interaction is independent of the other molecules and atoms that are around. That could be a very big assumption, because all the van der Waals interactions, all the discussion of the van der Waals interactions that we had in the last lecture, that always assumed that just two atoms were interacting one with respect to another. We didn't take into account any influence that surrounding atoms or molecules could have on that interaction. So that's another big assumption that we made, right? We've assumed these perfectly smooth interacting surfaces so we can do the integration analytically. Again, surfaces at the atomic length scale have atomic corrugations, right? So you cannot approximate a sphere by the standard formulas for spheres, right? There could be corrugations that our integration does not take into account, okay? And the other thing that's really evident is that these tip surface interaction energies, they obey different power laws, completely different power laws than the interaction energies between, let's say, two atoms or two molecules. So the atom-atom or the atom-molecule interaction was a 1 over r to the 6th. When you integrate that over a substrate, flat substrate, you integrate that over a spherical tip, the net interaction force is a 1 over d force, where d is the surface-to-surface separation. Right? So you're going from a 1 over r to the 6th to a 1 over d, completely different. It's just a function of the geometry of the tip and the substrate, right? So that's another thing that you learn from this discussion if you sit back and think about it. So, experimentally, how do we get at these interaction forces, right? Is there a way that, for instance, we can measure the forces that govern the interaction of two surfaces? And the answer is, one simple way to do that is to go after these macroscopic surface forces, right, which exist between interfaces, right? So if you have two substances, right, and you're allowed to vary the state of each substance, then the substance could either be a liquid, a gas, a solid, or a vapor. Those are the possibilities. And so you can start to ask questions about, you know, if you have an interface between two different materials, how much energy does it take to separate those materials? And the energy that it's going to require to separate those materials should somehow be related to the interactions of the atoms in one material versus the atoms in the other, right? You'd like to believe that, at least. So this is a common problem. I mean, our chemistry friends know more about this than possibly engineers and physicists, because they have all these surface energies that they like to talk about. Surface energies allow you to understand the shape of, let's say, a liquid drop on a solid substrate, right? Depending on the relative surface energies of the liquid and the solid, you can predict the detailed shape of a liquid drop on a substrate. So that's what we're really talking about here, right? And to try to make the discussion a little bit easier to understand, I'd like you to just think about a bulk solid that's comprised of a perfectly ordered array of atoms, right? And these perfectly arrayed atoms somehow interact one with respect to another. And I show that interaction by those little red ellipses, right, that are colored pink, right? So there's some interaction energy that governs this solid that's comprised in this perfectly periodic way. And it's a fair question to ask if I somehow come in and I separate the solid, if I drive a wedge between two rows of atoms, how much work, how much energy is going to be required to pull the surfaces apart, right? That's a measure of the surface energy of that solid, right? So you say to yourself, well, why would you require work to do that? Well, in the process of separating one surface from the other, right, you disrupt this periodic interaction of all the atoms, one with respect to the other, right? And now you've created an interface, and the atoms at that interface have nothing to interact with, right? It's clear there's a difference in how those atoms look compared to what they did, compared to the configuration they had when they were closely joined together. So in the literature of chemistry, that would be known as a dangling bond, right? There could be dangling bonds that protrude into the interface region in the process of splitting the solid, one's producing the surface in the solid by splitting it, pulling it apart. The energy required to produce that interface is something that we can possibly calculate using all these van der Waals interactions, right? And so there's a way to validate this very elaborate mechanism involving van der Waals interactions, because we just have to calculate the energies required to produce these surfaces, right? We can work backwards and calculate that using the van der Waals interactions. And the way that goes, right, is you define something called a surface energy gamma, right? Well, it's even simpler than that. You start off by saying that the amount of work you have to do to produce a surface is proportional to the area of the surface, right? So if you produce a surface that's, let's say, 1 square centimeter and you do a certain amount of work W, if you produce a surface that's got twice the surface area, produce an interface that's got twice the surface area, you'd expect that the work would double, right? And if you triple the surface area, you'd expect the work to triple. So there's a proportionality between work done and area created. And that's based on the number of molecules that are split in the process of producing the surface. I think that's a pretty intuitive concept. To turn that proportionality between work and surface area into an equation, you need a constant proportionality. Constant of proportionality is this parameter gamma, which is known as a surface energy, right? And it's a scalar quantity, and it basically tells you the energy that you produce when you split a surface. So you tell me the area of the surface that you want to create, you tell me the appropriate surface energy gamma, and then I can tell you how much work is going to be required to split the surface. That's the idea, okay? That's the idea. These surface energies are reasonably well known, right? The chemists, I mean, this is like a cottage industry in chemistry, I think, to be honest. They like to measure these quantities. And so you can go to the web page or to textbooks and you can type in different materials, liquid or solids, and you can get different surface energies. And the surface energies are basically telling you how hard it is to produce the surface. So materials that have high surface energies are going to be reactive, right? Nature's always trying to get to the lowest energy state. And so, for instance, if you produce a surface of gold, which has a surface energy of 1,000 millijoules per square meter, right, and you let that surface of gold sit in air or sit in ambient conditions, it's going to want to adsorb hydrocarbons which have a lower surface energy onto the gold surface to lower the net surface energy. So materials with high surface energies tend not to stay clean for very long. They will just scavenge contaminants from the atmosphere to coat them up, right? And so that makes the measurement of these surface energies difficult because you never know for sure whether your surface is clean and whether the surface energies that you're measuring are intrinsic to the surface or are they related to the contamination that's been deposited onto the surface. There's a question.
How is the surface energy of a solid measured?
Well, the surface energy of a solid tends to be measured by putting a drop of a liquid with known surface energy onto the solid surface, and then you measure, let's say, a contact angle that the drop makes with respect to the solid surface. And so you have to then, there's an equation by Young and Dupre that allows you to measure a contact angle, and you can work backwards and get the surface energy of the solid.
If the solid is not smooth and is porous,
Oh.
that would become more complicated.
Values. The values that you get are very, very sensitive to surface contamination, adsorbed contaminants, surface roughness, right? So if the surface is rough, you could get a different surface energy, different apparent surface energy than if the surface is smooth. So I think measuring these quantities and getting reliable numbers is difficult. Okay, I don't think it's a casual afternoon in the lab, right? I think you have to go after it in a serious way, but people do this for a living, and there are numbers that different labs tend to agree on, right? So, the point, all I'm trying to do is say that there's this thing called a surface energy. It's well defined, right? And it allows you to start thinking about these van der Waals forces in a different light. Because if I have a solid, okay, let's call it solid number 1, and I split it to produce 2 surfaces, right? Then the energy required to split that solid to make those 2 surfaces, well, I pick up a surface energy gamma 1 for the top surface, I pick up a surface energy gamma 1 for the bottom surface. The total area I create is 2, right? So the work required is going to be just 2 gamma 1 times the area that I produce, right? And that work is related ultimately to the how these atoms interact, one with respect to another. So we should be able to estimate that, right? We should be able to estimate that. Right? By calculating the van der Waals interaction between a block of material, which has a unit area, and a slab that's got, let's say, an infinite extent. So what I can do is I can go back and I can change the arguments, right? I mean, the geometry is different. I now no longer have a sphere. I've got a block of material. But I can still calculate the interaction energy between that block and the surface as a function of this parameter zeta. In this case, the separation is set equal to d. And what I find is I find that this plane-plane interaction is now this Homaker constant divided by 12 pi times a 1 over d squared separation, right? And my claim is that this number has got to be related to these surface energies, gamma, that you derive by splitting surfaces apart one from another, okay? Now, one issue is going to be what this separation d is, right? What separation d do I use when I evaluate this plane-plane interaction energy, right? And I have to go back and I have to refer you to the equilibrium separation between atoms, right? This, again, goes back to the previous lecture. We've got this this 612 Leonard-Jones interaction energy potential. The point is that the equilibrium separation between two atoms, according to this formula, is this parameter R star. It's also referred to as A0. It's the interatomic spacing between two atoms, right? So what I like to believe is, I like to believe that this interaction energy, van der Waals interaction energy, when two surfaces are separated by this parameter R star, so I let D equal to R star, I like to believe that that interaction energy is just the energy required to produce the surface, this dW11 that we were discussing in the previous slide. And dW11, if the two materials are the same, that's just 2 gamma 1. Gamma 1's the surface energy of that material. And so at the end of the day, what you have is you have a simple expression that relates this surface energy, gamma 1, to the Homaker constant, right? This parameter A sub h that governs the interaction between two solids, right? And so, in principle, if this is done carefully, right, by measuring this surface energy, you can work back, you can get a Homaker constant A sub h out, right? There's just some numerical constants that are involved. It's 24 over pi. You need to know the separation distance between these two solids, right? You got to know what R star is. That's hard to know, right? It's very hard to know that number. So there's probably going to be an effective R star. It's probably not going to be the lattice constant, the separation between atoms, neither the substrate or the tip. It's probably going to be an effective number, right? That's difficult to know from first principles. But the point is, this Homaker constant A sub h is related to something in principle that we think we know reasonably well. That's something easy to measure in labs. And you can find tables in the web pages that show you how well gamma agrees with Homaker constants A sub h. So, you know, this is a active area of research. People are trying to sort this stuff out in more detail. So this is one way to get at that parameter A sub h, which is really elusive, right? People always talk about it, but the issue is, how do you measure it? I mean, how well do you know it? Because if you don't know that, then it's hard to do a first principles calculation of how a tip interacts with a substrate. Okay? This is one way experimentally you can get at it. So that's the point of this little diversion. I had a slide in here where I actually calculate what typical value for this Homaker constant A sub h is, right? So if you tell me what the parameter C is for the Leonard-Jones potential, you tell me what the number density of atoms is. The number density of atoms is about 3 times 10 to the 28th per cubic meter. I can calculate these Homaker constants, which have units of energy, joules, right? Those numbers come out to be about 10 to the minus 19 joules, typically. And so for most solids in the literature, you'll find Homaker constants that range roughly between 0.4 and 4 times 10 to the minus 19 joules. And if you have the reader that we handed out in the first day of class, there's an article in that reader by Butt, Capella, and Kappel. If you look on page 50, you will see a long table with references, right? So he actually refers to the original literature, and this long table lists all these Homaker constants for different systems. Right, so this is something that you don't learn in your introductory physics or chemistry classes, right? This whole idea of a of a van der Waals force and Homaker constants, and how the interaction between electrically neutral solids, what governs that interaction. That's something that was not really well studied before, let's say 1990, but with the advent of atomic force microscopy, this this topic became something that lots of people had a great interest in. So I tried to give a little background, a little history, and hopefully maybe you can understand the discussions that you find in the literature a little bit better because of this lecture. I should say that in general, how two electrically neutral solids interacts, right? In general, that is a complicated problem, and it involves the detailed geometry of the two bodies. And so if you've seen his Machiavelli's book, right, he's got a very nice table where he shows interactions between various objects, right? So I think in this lecture I covered the atom surface interaction, and I talked about the sphere surface interaction. Those were the two that I went through. I also did the plane-plane interaction, which is the last entry in this table. But depending on the geometry of the two objects that interacts, right, you got to do the integration, and you're going to get different force laws, right? And it just turns out the two or three that are most interesting for our purposes is the sphere plane and the atom surface interaction. The one that's the most fundamental is this surface interaction. That's the surface energy. That's really the most fundamental parameter that you can measure experimentally, right? So I just wanted to make that point. The next topic is kind of a way to get at these plane-plane interaction energies, which are the fundamental interaction energies, right? These plane-plane interaction energies are governed by this, in principle, they're governed by this surface energy gamma, right? And the question is, can you do a measurement with a tip that allows you to learn something about how two planes interact, right? And this guy, Derjagan, comes up with this very interesting observation, and he says that, hey, look, if you measure the force that a sphere interacts with a plane, right? If you can measure that force, and of course you can measure that force with an AFM, with an atomic force microscope, right? You can get at this much more fundamental plane-plane interaction energy by just multiplying the plane-plane interaction energy by 2 pi times the radius of the tip. Okay? So this is yet another way to get at the plane-plane interaction, which is really a fundamental quantity. And what it says is, you take a sphere and you push the sphere onto a plane, and then you measure the force that's required to separate the sphere from the plane. And by the magic of the algebra involved, it happens. It just turns out that separation force is just 2 pi times the radius of the tip times the interaction energy between two planes. So the implication is, if this approximation is valid, right, just by measuring the liftoff force of a sphere from a plane, you can infer back to the interaction energies that two planes have. The interaction energies that two planes have is this fundamental quantity called the surface energy, okay? And it's just a numerical coincidence, I believe, that this happens. Now, this approximation requires the plane and the sphere to be rigid. If the plane or the sphere deforms, then Derjagan's approximation is no longer valid. Okay? So if you are in the business of AFM, right, and you start to measure liftoff forces of AFM tips from substrates, and you want to use this approximation, you have to convince yourself that the tip is very rigid and the substrate is very rigid, right? And to be honest, the next part of this lecture and into next week, we're going to talk about how valid this interaction between a sphere and a plane is. can we really approximate that as two rigid objects, two perfectly rigid objects that don't deform? Right? We're going to discuss that in a little bit more detail. And in the process of doing that, we're going to talk about contact mechanics, which is, again, a problem that probably the mechanical engineers understand better than the physicists or the chemists or the electrical engineers. So we're going to do a little bit of contact mechanics in the remainder of this lecture, and we'll have to carry it into next week's. Was there another question?
Yes, so it would be kind of difficult to apply this approximation for soft molecules like organic molecules.
Oh yeah, it would be. So the question is this Deryagin's approximation valid for soft polymers, let's say? And the answer would be clearly no, right? It doesn't stop people from doing it, right? Somehow that still gets published in the literature, but clearly it doesn't make any sense, right? So we'll talk about soft substrates, right? Stay tuned. We'll discuss that in a lot more detail. Okay? And then I guess I should just say that you can show, right? You can show that if you have two spheres interacting, sphere of radius R1, sphere of radius R2, right? Deryagin's approximation is slightly modified. You now have to put in an effective radius, right? So you have to replace R tip by the product of the two spheres divided by the sum of the radius of the two spheres. So there's still a way that even if the substrate is not perfectly flat, if it's got some curvature to it, there's still a way that you can measure the sphere-sphere interaction force, right? How much it takes to separate two rigid spheres, and you can relate that back to this fundamental plane-plane quantity. Okay? So I try to make the case a little bit more clearly here, try to discuss some of the implications of this approximation, right? Technically, if you follow the lecture notes, we've only discussed the special case where U is a constant divided by R sub n, where n is an integer. But this approximation is valid, it turns out, for a variety of different force laws. So it's pretty general. It also assumes that the two spheres are the sphere and the plane, right? If you're measuring the separation force between a sphere and a plane, or between two spheres, right? It assumes that those two things are in contact, right? So that means that the separation, D, between the two surfaces is this quantity R star, which is determined in principle by the Leonard-Jones force law, right? So any contamination, anything that separates the two spheres, so let's say you have a water layer or a hydrocarbon coat on your surface, right, that separates the sphere from the plane, then this approximation isn't going to work anymore, right? So that's one thing that really is difficult, right? The other thing is that the reason it's interesting is because it allows you to estimate this work to produce a surface, this D11. That's that plane-plane interaction energy. That's this surface energy, D11, that we talked about earlier, right? That's a fundamental quantity. So if you can ever achieve experimental conditions where you can make an accurate and reliable measurement of the separation force between a sphere and a plane, in principle, your measurements can be used to infer these fundamental surface energies, right? So that's why we mention it, but I think it's hard experimentally to pull off, right? So we alluded to the fact that when the tip comes into contact with a substrate, right, we're assuming that contact is reasonably well understood, right? And the question is, how do we model it? How do we think about it in more detail? And you got two choices, right? One choice is you can think of the tip as a bunch of atoms, and you can think of the substrate as a collection of atoms, and then you can think of the interaction between the tip and the substrate as a collection of atom-atom interactions, or molecule-atom interactions, depending on what your substrate is made of, right? That is a very fundamental way to think about it, but it's very hard to make progress because you then have to do very detailed calculations of all these atom-atom or atom-molecule interactions. You have to know where the atoms are located, and often that knowledge is not there. But at a fundamental level, that's what's really going on. Our friends in the engineering community say, well, maybe, you know, if the contact between the tip and the substrate involves tens or hundreds of atoms, right? If there's a macroscopic number of atoms involved, then maybe we can just use continuum models. We can model the tip as a continuum sphere. We can model the substrate as a flat plane. And we maybe can use continuum elasticity to discuss the interaction of the tip with the substrate. So I think the physicists and the quantum chemists tend to look at AFM in terms of atom-atom interactions. I think all the people in the engineering disciplines tend to look at the tip-substrate interaction as a continuum interaction between spheres and planes, right? And all you can do is do experiments and pursue the models and try to understand which model fits the experiment the best, right? So we're going to take the point of view of following the continuum elasticity models to discuss the contact between a sphere and a plane. And what we're interested in here, let's be clear, we're interested in how much does the tip deform when it comes into contact with the substrate. We're interested in how the substrate deforms when the tip comes into contact with the substrate. We're interested in any adhesion forces that might develop between the tip and the substrate. All these things are very fundamental, very interesting quantities. It's just how do you extract that information? What theoretical models do you use when you make these measurements in an AFM, right? So we're going to try to develop these contact models, just describe them. They've been developed in the literature. We're just going to rely on the work that's been published. And then we're going to also say that this Veda model that Professor Rahman and his students have developed, right? This Veda model will incorporate all these models of continuum contact in the software. So you don't have to write computer programs to interpret your data using these models. You can actually use the mathematical models that are already in the Veda software and use those mathematical models to try to explain the liftoff forces, let's say, that you measure experimentally between the tip and the substrate. So that's, you know, there's going to be about 2 or 3 lectures just on Veda in the future in this course, and so we'll get into that in much more detail. So I think I probably ought to stop because my time is out. If you come back next week, we'll talk a little bit about these contact models. We'll just give you the main results and try to describe the approximations and assumptions that these contact models entail. And then we'll move on to Professor Rahman's lecture about measuring tip substrate forces and liftoff forces. So thanks for coming today, and we'll see you all next week.